Okay, so today I'm going to talk about some Bayesian methods for networks. This is somewhat of a didactic talk. It's going to sort of gradually build up a class of models that I've found to be very useful for analyzing a certain type of relational or network data. And so I'm going to start off just talking about a very simple kind of statistical problem, one that we're very familiar with, which is regression, and sort of build up from there in a network context. And then I'm going to talk about using Bayesian methods to accommodate quite a variety of different network types. And so this was something that came up in the workshop of 2 weeks ago, where we were mostly talking about mathematical models for graphs, but it was alluded to on several occasions that much of the actual data we see are not graphs. They're valued, ordinal, or even censored types of relational data. So I'm going to talk about that. And then I will discuss latent variable models and talk about some known models, and also discuss a few less well-known results. One particular result that I want to really emphasize. Okay. So for the purpose of this talk, relational data consists of a set of units or nodes or objects and a set of measurements on pairs of objects. Okay, so we have an index set A, and we have observations on the A cross A. And so some examples are, for example, international relations data, where we have a set of countries, and Yij is some sort of measurement between pairs of countries, such as an indicator of a militarized dispute or the amount of trade between two countries in a given time period. There's other networks, social networks. You could have a set of IV drug users, and Yij might indicate some sort of needle sharing activity between persons I and J. And another example from biology, we might be interested in looking at how proteins bind to one another. And so this is a well-studied category of networks. You have a bunch of proteins, and you examine the binding behavior between proteins. And here's a non-example. So at least for the purpose of this talk, this is not going to be considered a network. You take a dependence graph. In other words, you have a bunch of variables. The index set are the variables, and Yij is the presence of high correlation between I and J. I'm sort of leaving this out because this is multivariate data, and the sort of relations between these variables are constrained to be different than they might be constrained in these other examples. For example, a covariance matrix is positive definite. Okay, so I'm not going to be talking about these types of graphs. Okay, so here are two plots of two different real networks. The one on the left is a protein binding network, and the one on the right is a social network between high school students. And they look different, and we could each individually sort of describe how they look different to us. And we want to make this more formal in data analysis. We'd like to quantify the ways in which these are different. In particular, we'd like to quantify, for a given network, we'd like to quantify the patterns in the network. So how should we summarize such a network? So there's a literature on trying to think of good global descriptives of these networks, such as sort of the amount of transitivity or the amount of reciprocity in a network, or some sort of clustering coefficient. But oftentimes, we are interested in local features of networks, that is, identifying particular nodes, seeing how nodes differ from one another. So which are the popular nodes? Which are the sociable nodes? Are there groups of nodes that interact at a high rate with one another? Are there nodes that have similar characteristics? And additionally, we often have covariate information, and a problem that a lot of applied researchers are interested in is figuring out, why do two individuals have a tie? And so we'd like to identify explanatory variables, node-level predictors perhaps, or dyad-level predictors that relate or are associated with network relations. Okay, so I'm going to sort of focus on this last approach to begin with, And so I'm going to put things in sort of a regression framework. This is sort of how I got into the field. One of my early collaborators was a political scientist, and he was fitting regression models with network data. And so you might have data that look like this. Up here you have a sociomatrix Y, so a square matrix with, I should have an undefined diagonal here, but I didn't put that in there. But we might have missing values, some NAs. And we also might have an array of explanatory variables. So here I've written these x's are boldface, so you should recognize those as vectors. So for each pair of individuals, we have a vector of explanatory variables. So we have some explanatory variables, vector xij, to help predict or to explain the relationship from person I to person j. And so we might want to have a basic generalized linear model to describe these relations. So we might have 0, 1 outcomes, binary outcomes, and so we might fit some sort of logistic regression model. Or we might have counts. So we might fit some sort of Poisson model or zero inflated Poisson model. So yeah, this plus sign isn't to be taken too seriously. The model is that the outcome depends on this sort of linear predictor plus some randomness. Okay, so why a model? So a model can provide many things, so one of which is a measure, some sort of interpretable measure of the association between the explanatory variable x and the outcome variable y. We can get estimate beta hat. We can get a standard error for this estimate describing other plausible values of beta. We can get imputations from a model. So often models provide good predictive performance. So we might want to predict missing entries of this matrix here. We can also get a probabilistic description of network features. So we saw network Y. What are other networks Y tilde that maybe could have happened under a similar process? So these are things that a model can provide. And so a GLM, some sort of GLM seems like a natural first attempt at modeling such data. If you have binary data, logistic regression, probit regression. If count data, maybe some sort of Poisson, some other type of count model. Now, what makes network data different from other types of data is that almost every network I've ever seen shows evidence against the independence of the randomness. Okay, so in this setting here, there's EIJs. You almost always see evidence that these are not sort of IID deviations in any way. And so we know that if we don't account for dependence, all sorts of terrible things can happen. So we can get biased effect estimation if we have a non-identity link in our GLM. We can get uncalibrated confidence intervals, and we can get poor predictive performance. And perhaps most importantly, we get inaccurate descriptions of network phenomena if we just ignore the dependence in this randomness part. And often this is the most interesting part for many people. So, okay. So what I'm going to do, we're going to start building some models based on this issue. So we're going to test for and model some important features, some important forms of network dependence. So here's a data set. Notice it's not a graph. Okay, so here's the first 5 rows and 5 columns of a sociomatrix, but it's not a graph. These are trade measurements, logged trade measurements between pairs of countries over a 10-year period. I got from my colleague Mike Ward at Duke University. And he was interested in associating trade flows between countries with explanatory variables. So in his field, they often come up with theories for why some countries trade more with other countries. And they like to quantify these theories, test their theories, and evaluate them. So until surprisingly recently, the approach was to take this n by n, so actually it goes much beyond 5, okay, so you can take all countries in the world. For this example, I'm just using the top 30 economies. But you could take your n by n sociomatrix, you have n squared essentially measurements, and you just fit a regression. You have n-squared outcomes versus n-squared predictor variables. And some of the predictor variables were things like measurements of the amount of conflicts between pairs of countries, the distance, geographic distance between countries, the number of shared intergovernmental organizations, and a measure called polity, which is a measure of how democratic the countries were.
So what are these correlations?
Pardon?
What are these correlations?
These are not correlations. They are log trade flows. So this is this here is a scaled measurement of the amount of trade between Argentina and Australia over a 10-year period.
How's it scaled?
It's not symmetric, right?
Pardon?
It's not symmetric.
Absolutely not. So it's exports from one country to another country. Yeah. So I use a normal scores quantile transformation.
But, I mean, is it standardized by the size of the economy?
No, it's not. And that's kind of important to what's going to come next.
Okay, so 1.76 means it's kind of 1.7. You look at the 30 by 30 or whatever it is.
Yeah.
It's 1.76 standard deviations to the right.
Yeah, that's right. Okay, so we can fit just a regression model to these data, and I'm fitting a regression model with this. So I'm also using this talk to highlight a software package that I spent a lot of time working on, along with some colleagues. It's called the Additive and Multiplicative Effects Package for Networks, okay? Or AMEN, okay? So my first software package was for semi-parametric copula estimation, and it was semi-parametric Bayesian Gaussian copula estimation, and I called it SBG-COP, which is the worst name you could ever have. And it was Adrian who told me, like, you need to have a good name for whatever you do. And so, as I will describe coming up, this AMEN package uses MCMC. So the idea is you start your MCMC and then you pray that it converges. Okay. But this package can also do simple things like fit just ordinary regression. And it does this in a Bayesian way. You get a posterior mean, posterior standard deviation, a z statistic essentially, and converts all this Bayesian stuff into a p-value. And see somebody cheering, somebody frowning. Okay.
This is only for the first three columns.
Yeah, that's right.
I'm going to ask a question about just the data. So
Yeah.
Are these covariates you created, or are these things that the political scientists had already given you?
They had given me these things, yes. Yeah. Okay. And not surprisingly, I mean, you could see some of the effects. So as countries get further away, as the distance increases, for example, the amount of trade decreases. And there's some other things in here. Okay, so is this a good model? Is this a good representation of the network data set? So one way to evaluate whether or not your model is a good representation of your data is to look at what your model would predict. See what other types of networks that your model would predict. And so one way to do this is with a posterior predictive check. And so you pick a summary statistic, G, which maps a network to some real valued number. And what you do is you simulate a new network from the posterior predictive distribution of the network given the observed network. In other words, roughly speaking, you estimate the parameters in your model with your observed network, and then you use those parameters to predict a new network, Y sim. So now you have a new network, Y sim, and you compare the statistic for Y sim to Y observed. So here are three network statistics provided by this package. There's another network statistic which I'll get to later. So one is the standard deviation of the row means. So you can think about this as a standard deviation of out degrees if you want. And another one is a standard deviation of the column means. So these are representing heterogeneity between the nodes in terms of their activity. So this is heterogeneity of the nodes in terms of their outgoing activity. This is heterogeneity of the nodes in terms of their incoming activity or incoming trade flows. And then there's dyadic correlation. which is just a correlate. In this case, it's just a correlation between Yij and Yji, taken averaged over all pairs. Okay, and so these histograms represent the predicted values of these statistics under this model. And the dashed red lines are the observed values. Okay, so the G of Y observed is here for this statistic, and here's what we predict from this model. Okay, and so we see that in terms of all three of these statistics, the model performs poorly. So the model is not able to represent these features of this data set. So the model is not able to represent the amount of degree heterogeneity, outgoing degree heterogeneity, export heterogeneity, import heterogeneity, and pairwise correlation. Okay. All right. So, so this shouldn't seem that strange, right? If you think about the data in terms of this matrix. So that's why I like thinking in terms of matrices. So I went to a graduate school that was focused on agricultural statistics. And every matrix was like, took a NOVA class. It's like fertilizer by crop type, called a variety. Fertilizer by variety. And anytime we were trained, anytime you see a matrix, you think row effects, column effects, okay? So recognize that when we look at the data in terms of a table, right, it's a matrix, right? So there's rows and there's columns. So it's not surprising that there should be some sort of, within row similarity, okay? There might be some within row similarity. The values within a row might be more similar to each other than they are to values in a different row. And within row similarity, this is the same thing as across row heterogeneity, right? We also might have within column similarity and within dyad similarity. The two observations within a dyad are more similar to each other than they are to other observations. Okay. So this leads us to, in my mind, one of the first types of models for relational data. It's called the social relations model. And it wasn't really developed for what we might say network data. It was developed for type of experimental procedure in psychometrics, where they brought in undergraduate psychology students and said, in order to pass the class, we're going to run some experiments on you. And they brought undergraduate psychology majors into the classroom and had them do things with each pair of students would do things with each other. And so the psychometricians came up with a model to analyze this type of data. So you can now see that type of data is sort of a matrix data where you have an index set along the rows, an index set along the columns, and they're the same index set. Okay, so the idea behind this model was that the goal was to decompose the variance. It's a very ANOVA style goal. The goal is to decompose the variance around the overall mean into several parts. One part describing heterogeneity across the row means, heterogeneity across the column means, and correlation within row and column means. So somebody who's very active as a sender might also be active as receiver. And then also correlation within a dyad. Okay, so that was the social relations model, and these researchers developed an ANOVA decomposition which could estimate these sorts of correlations. So here's a random effects representation of this social relations model. So it's fairly intuitive. It's for those of us familiar with network data, it should make total sense. So the idea is we have some network data set, we have some baseline mu representing the density or sparsity of the network, and then we have some Eij, which represents residual variation. And so the residual variation gets decomposed into parts, a row effect, a column effect, and then within dyad effect. And so the idea behind the social relations model is that each individual has a pair of random variables, A1, B1 for person 1, and those might be correlated. Okay, there's some variance for A1 for the A's, there's some variance for the B's, and some covariance between them. The covariance representing whether or not people who send a lot of ties also receive a lot of ties. It could go the other way, so it could be anti-correlated. And then also some within dyad correlation. Okay, and then there's other people who did various versions of this Including developing some MCMC routines for this and maximum likelihood estimation. Surprisingly, people weren't using this for regression. I mean, it's possible that I overlooked the literature a little bit, but I think the reason is that the ANOVA decomposition is really clean and beautiful. It's like you do this beautiful ANOVA decomposition, all the parts just fall out. And then as soon as you put in regressors, it totally screws up the decomposition. So it's not pretty anymore. Okay, so, but I mean, it's evident you can easily put these in a model to account for dependence. Okay. All right, so in fact, so we can fit that model for the trade data with this command in the AMEN package. In fact, that model, the social relations regression model, is the default model for these data. And I'll show you some other models it fits as well. And if we, so it gives you the summary, and now things have changed a little bit. So the number of conflicts between countries no longer has there's no longer strong evidence of an effect of this. The standard errors have generally gone up. Our uncertainty in these things has gone up. Maybe that's a bad thing, right? But if you think about it, we started with saying we had n squared independent measurements, right, to estimate our regression parameters. Now, if there's a lot of within dyad correlation, right, we don't really have n squared measurements. We might have like half that many if our correlation is high, okay? And so recognizing these things is important. You don't want to say you had twice as much information as you actually had when you are reporting these values. Okay. So does this model fit? So let's look at our summary statistics. So this is from the ordinary regression model. Okay. So now let's simulate from the social relations regression model. And here's what we get. So the blue histogram are the simulated values from the social relations regression model. And the green histogram is from the ordinary regression model that didn't account for any sort of dependence in the data. And what we see is that the social relations regression model really nails the observed values of the statistics. Okay? And so this model is able to represent the network in terms of these particular features. Okay. All right, so network data, we're focused a lot on maybe binary outcomes, non-Gaussian outcomes. And so it's pretty easy to formulate the social relations regression model to extend that to accommodate binary data. So just remember, this isn't a network model here. This is just probit regression model, right? So in probit regression, one way to write probit regression is that you have a bunch of standard normal outcomes, and then you have some latent variable zi, which is a linear predictor plus some standard normal deviation. And what you observe is just the binary indicator that zi has exceeded some threshold, right? So that's just the latent variable representation of a probit regression model. So straightforward to use this concept to extend the social relations regression model to binary data using a probit link. So the idea is, as before, so you're observed in this model, the observed outcome yij is the indicator that zij is greater than 0. And then you model this unobserved latent variable in terms of a linear predictor plus noise. And we just use for this noise, we use the social relations covariance model. Right? So this will induce in our binary data row dependence, column dependence, and within dyad dependence that we get from the social relations model. This is very similar in spirit to some ERGMs, exponentially parameterized random graph models, the P1 and P2 models developed by these researchers here. So these models, that's sort of your first step at modeling network data in my mind is getting that row heterogeneity, column heterogeneity, and within dyad correlation. Those are that's the low-hanging fruit. Those are the things you want to nail right away. Okay. Okay, so I thought about the title of this workshop and the title of my talk, it was Bayesian Methods for Networks. And I was trying to think if there's a particular reason to use Bayes for networks other than that, that you should use Bayes for all of your data, right? And I couldn't come up with anything particularly profound. And for me, I'll sort of try to summarize this at the end, but I struggled a little bit trying to come up with like some really knockout, profound reason to use Bayesian methods. But for me, it's mostly pragmatic. So maximum likelihood estimation is really problematic for some non-Gaussian random effects models. So for example, I showed you that random effects model, the social relations regression model. You can actually, with quite a bit of work, you can encode that in, for example, the NLME package or LME4 package that has been developed extensively by Doug Bates and others. But it just barfs. It just will not do it. Why is that? So the likelihood involves some very high-dimensional integrals, and in particular, the methods for doing a lot of GLMs with random effects use Laplace approximations, which some of which are good, some of the approximations are good, but some of which just fail. And you can very clearly identify where they fail. And so, so there's problems with that. So alternatively, you can use Bayes estimation. You can replace doing these high-dimensional integrals with Laplace and instead use Markov chain Monte Carlo. And as we'll see in the next section, there's some other good reasons, or the Bayesian approach accommodates other more challenging types of network data. Okay, just to very quickly show you how it might work. So here's the model setup. So you have some, in sort of this orangey brown are the observed items. You have some observed outcome and some observed explanatory variables, and you need to get the posterior distribution for all the quantities in green. And this is pretty easy to do. So the regression effects and the additive random effects, that's all just linear stuff that's really very fast. And these covariance matrices are low dimensional. Those are very easy. The hard part is simulating these latent variables. These are the latent variables in the probit representation of the model. And you have to simulate from correlated Gaussians, which can be challenging. So right now I'm working with a student on faster ways of doing this, but it's still work in progress. Okay, but this is all implemented in the AMAN package. I want to advertise again. I'll continue to do so. It's on CRAN and GitHub, and there's a 50-page tutorial that I wrote. So please read it, because I spent a lot of time writing it. All right. If you teach a class on network analysis, it has lots of examples in it, so maybe that'll be useful. Okay, and here's what it looks like, just to prove that it looks like a real R package, right? So all this stuff, I didn't make this up. This came right out of what happens when you type AIM. Okay, so there's lots of options here, including one called model. Okay, and that's what I want to focus on now. So moving on to the next section of the talk. So model equals norm. So normal, NRM, that stands for normal. That's the model we use to analyze the trade data, which we assumed had additive Gaussian errors. So the AMAN package handles lots of different types of models, and the goal was to accommodate lots of different types of network outcomes. And so why is this? So if you look at, like, anytime you see something about relational data on Nature or Science or some magazine, show a big graph. Okay, show a big graph. And why do we show big graph? Because graphs are much prettier than tables of numbers, right? And so the literature seems to suggest that almost all network data is just a big graph. Okay, so this is our sample space here. So our sample space is the set of square binary matrices with a missing diagonal. And that's all the possible things that could happen. I'm tempted to go to this link here. Yeah, so this is a really neat data set, or sorry, website. It has maybe 100 network data sets. And if you go through, has all these network data sets, and it says what type of network or relation it is. So the first one is a symmetric binary matrix. And then the second one is, I can't find it. All right. So the next one is non-symmetric valued. Another one, non-symmetric valued. Here's a different one. Symmetric valued, symmetric rankings, symmetric valued. Okay, so if you go to this data set, I think I did it once. I counted the fraction of times it wasn't binary, and it was like, 78% or something. So in fact, a large fraction of the data we encounter is not really binary at all, and it's something else. And so what do you do? So you teach an applied statistics course. You have all these methods for Gaussian data, right? And so so if you have this method for Gaussian data, if your data aren't Gaussian, what do? You transform it, right? So if we had a model for network data and it's for binary data, but our data are not binary, well, what can you do? Well, you can transform it, right? You apply a transformation. So this is what we see a lot. People will threshold some their observed valued relations at some value, and then turn it into a binary network, and then analyze it with their binary network method. So I would argue against this. So unlike a square root transformation, this is not invertible, right? So if you go from continuous measurements or valued measurements, and then you turn it into zeros and ones, you've just thrown away a lot of information, right? You can't go back. And so you're potentially losing a great deal of information from the data, and so maybe we should try a little bit harder to work on models that accommodate non-binary outcomes. So I want to show you one particular extreme case of non-binary outcomes. It looks like it might be close to binary outcome, but it was sort of challenging to deal with. And so we had to come up with a new way of analyzing this type of data. So this is data from a high school friendship network among females, this particular data set. So there's 646 female study participants here. And so this is the network, so to speak. And we also have information on the students' smoking, drinking, GPA, stuff like that. Their after-school activities, in fact. And so here I've made a histogram, basically, of the out degrees and the in degrees. Okay, so the in degrees, you can see this. One individual is very popular. They received a lot of incoming friendship ties. Some people didn't get any. What about the out degrees? So anybody see anything funny about the out degrees? Yeah, so there's a lot of people who sent 5 network ties, but nobody sent 6. So why is that? So in fact, that's an artifact of the way the data were gathered. Okay, and so this is true of quite a number of network data sets. So each study participant was asked to nominate up to 5 friends from a roster of students, and then asked to rank order their nominated friends. Okay, so what are the data? So I'm going to code these data as follows. So Sij is student I's score for student J. So we're going to say Sij is 0 if J is not nominated by I. Okay, it doesn't mean that I doesn't like J. It means that J is not in their top 5. That's all it means. And so we're going to have a 1 if J is I's least favorite nominated friend, and their best friend is given a 5. However, some students didn't nominate 5 friends. Okay, so some people only nominated 3 friends. Okay. All right. So these data are not binary. They're ranked. They're non-binary. They're also censored. Okay, and so, so this is challenging. But a lot of studies use this type of data gathering scheme. So, for example, this is used in the widely known AdHealth study. And AdHealth stands for adolescent health. But you know that adolescent doesn't have two Ds in it. Or it does, it has three Ds in it. But it's spelled AD something else. But then they thought it sounded better if we call our study AdHealth, like we're adding health to the students, right? That sounds better on your human subjects form. So there's other studies that use this scheme, Prosperous study, Netherlands school study, many others. The classic Samson's Monastery study uses a scheme like this. Okay. So here's the kind of data we have, and here's what would happen if you just sort of dichotomized it, right? So maybe you have this person here. Suppose you had a study where people are allowed to nominate up to 3 friends. Okay, so maybe this is person 1's vector of outcomes. So they said this person 6 is their most liked friend, and then they have another person they ranked 2nd, and then somebody else they ranked 1, their lowest nominated friend. But then they weren't allowed to nominate anybody else. So they may or may not like these individuals here. But that gets translated into zeros. That gets translated into saying that this person doesn't like these other individuals. Okay. Whereas you might have somebody here, this person nominated 2 people and didn't fill up their spots, right? So in this case, this person's data are not censored. Okay. So this is kind of funny. Some people's data are censored, some people's aren't. So, but anyway, this dichotomization is problematic. So first of all, ignoring the ranks, that's inefficient. So we're throwing away some information. But in my experience, the more serious thing is that ignoring the censoring can result in very misleading inference for particular parameters in the model. So what could go wrong? So just imagine you have some model like this. You have your outcome, there's some overall mean, there's some effect of some row, some sender-specific variable, some receiver-specific variable, maybe some dyad-specific variable. So what happens if you ignore the censoring in the rows? You're going to underestimate the variability of the out degrees. Okay, so the true affinities of individuals for another are reduced. Or the variability of that is sort of thrown away. Okay, and we're pretending that there's less variability, right? So if you go back to this histogram here, if you didn't force people to only have 5 nominations, we would expect that this histogram would look different, right? So there'd be more heterogeneity. Okay. Okay, so what we're trying to do is estimate this actual heterogeneity. Okay, so the guess would be that we'd get biased estimates of anything that has to do with a row effect. Okay, so the data are ordinal and censored, and we tried to develop a likelihood that can accommodate this type of data. So just using the likelihood from like a binary type of model, binary dichotomization of your data, is going to ignore the censoring and ignore the ranking. So we wanted to come up with a method that could take both of those features into account. So here's the approach we took. So we imagine that there's some underlying matrix of affinities that each individual has for each other individual. And these are unobserved. And then the survey or the study tries to get at what these are by asking people to nominate friends. And so we observe these scores, right? We observe these scores. And so hold on. So the idea would be that if Yij, somebody might have a positive affinity for somebody, but if they're not in the top 5 affinities, then it's not going to be recorded in this score. Okay. So our idea is that we might have some natural model for what people's affinities are for each other based on their characteristics and so on, but we don't get to observe the affinities, we just observe these scores. So what do the observed data, the scores, tell us about the affinities? Okay? Well, if somebody scored somebody as a friend, so if Sij is greater than 0, then had a positive affinity towards this person, right? So that much we can take for granted. On the other hand, if Sij is 0, so person I did not score person J, but they could have, their out degree is less than the maximum allowed, so they had another slot on their list, right? So if they didn't score them and they could have, then that tells us that Yij is less than 0, that they did not have a positive affinity for this person. And then finally, if I scores J higher than they score K, then that tells us that Yij should be larger than Yik. So that's what the scores tell us about the affinities. Okay. All right, so how can we use the information about the scores if we have a model for the affinities?
Peter,
Yeah.
But when you have the 0 on the right-hand side of both 1 and 2 there, that's sort of suggesting of equations 1 and 2 that everybody is using the same sort of definition of the threshold.
Sorry, I don't understand. What do you mean on the right-hand side?
But you're saying Yij is greater than 0, but in the second case, in equation 2,
Yeah.
you're saying Yij is less than or equal to 0. But that threshold is somehow person-specific as well.
Yes, that's right. And it ends up being person-specific in the model because we're going to have a person-specific intercept. Yeah.
Okay.
Okay. All right. So how do we use these scores to do some estimation? So the idea is as follows. So we have these observed scores, and let's let f of s, let's let that be the set of all real valued matrices y such that these three conditions hold. Okay? So that's the idea, right? The scores tell us, these scores, the way that the data were gathered tell us that if we see some scores, the scores tell us this about the y's, the affinities. Okay? So the set of possible affinities are the set of y's such that these three conditions hold. So observation of S tells us that y is in this set. Okay, so what is our likelihood? Well, the likelihood is the probability of the observed data, right, for a given value of the parameters. So if we have a model for the affinities, then our likelihood, well, it's just the probability that y is in this set. That's what we observed. We observed the event that y is in this set, essentially. Okay, and so the probability is then the integral of p of y given theta over this set. Okay. So that's what we call, so this survey scheme is called a fixed rank nomination scheme because you have a fixed number of people you can nominate and rank. Okay, so we came up with this likelihood for this type of data. There's other types of likelihoods you could use. You could just use a rank likelihood. So in other words, you just say, well, I saw this person I scored J higher than K, so that just means that Yij is higher than Yik, and ignore the censoring and things like that. Also, there's the binary likelihood. This is a likelihood you get if you just sort of ignore the censoring. And so there's two other likelihoods you could use. And I'm going to, so here's the idea. So think of this whole space here as a set of all y's, all real valued sociomatrices y. So if we get some scores S, that tells us that the y's are in this set. Okay? And if we just use the rank likelihood, tells us that we're in this set, which is less precise. So just using ranks is valid, but not fully informative. Now, how about if you just censored your data? Or sorry, not censored, if you just dichotomized your data? Yes?
Would it be better if the social scientists actually asked for an affinity for each of the ranked individuals so that there was a maximum of affinity of 5? So the person who nominates only 2 friends might actually assign affinities of 5 and 4 or 5 and 5.
Yeah. I think there are definite improvements that could be made to these, and in particular, I think what you're partly alluding to is that the ranks might even get kind of noisy, and the difference between a 4 and a 5 might be kind of meaningless at the end. And I agree with that. So maybe I can add a comment. Taking account of the censoring is the most important part here, and the rankings are less important in terms of the bias you get, and also, like you say, more suspect, I would say. Yeah. So here's what happens if you ignore the censoring. These pictures aren't really accurate, right? This isn't what the shape of the set is. But the point is that if you just if you dichotomize your data, you're saying certain things are impossible which actually are possible, and other things are possible which are impossible. So you get a likelihood which is bad, okay? All right, so the use of the binary likelihood is not valid in this sense. You're ignoring the censoring. Okay. Okay, so you can use this likelihood which accommodates the censoring, and here's how to do estimation using this type of likelihood. So it's based on sort of assuming that given this observed data, these affinities lie in some set. Okay? And what we want to do is we want to integrate over that set. And so I don't like to integrate, so I do MCMC. So here's how you can do it. So you have this model, you have some model for the affinities, maybe a social relations regression model. You have your data are that y lies in some set, and so you want to estimate for any given value of theta, for a prior over theta, you can get a posterior distribution for theta conditional on y lying on this set. And it's pretty straightforward. First you simulate theta from its full conditional distribution given some values of y, and then given theta you update the yij's. And you're sort of averaging over all the possible values of the sociomatrices that could have occurred given your observed scores. Okay, and this can be done in the AMEN package. So this model is using it's a fixed rank nomination model. It's not really a model, it's more of a likelihood, I would say, which is sort of a model. Okay. So in the interest of time, I'm just going to kind of just give you the main points. When the amount of censoring is large, the heterogeneity, the censored out degrees, is low, and you're going to assume that actually represents the actual heterogeneity of affinities, and in fact, you're going to confidently underestimate this heterogeneity. And we can show this analytically and with simulation in the paper. Just in terms of the actual data analysis, it's a little bit hard to see. We fit a social relations regression model. We had lots of explanatory variables. And basically, if you ignore the censoring, this B here are the estimates, and you can barely make out a 95% confidence interval. These are the estimates you get if you ignore the censoring. And basically, you detect no effects of any row effect. Okay? Whereas other methods that account for the censoring do. And actually, you get the estimates for everything else are also, if you ignore the censoring, tend to be biased towards 0. Okay. Okay, so the take-home message there is that inference should account for the mechanism by which the data were gathered. So sometimes we get some network data set off the web or something, and you just sort of take it out of context, right? So it's important to recognize the context in which the data were gathered, and this can dramatically change the inferences that you make. So certain types of sampling schemes can be accommodated with these set-based likelihoods. Okay, so now for the last bit of the talk. So up till now, I've just been talking about a very simplistic model for representing dependencies in network data. And this is just, it's like a standard random effects type of approach. We've just been modeling row heterogeneity, column heterogeneity within dyad similarity. So in other words, covariances and correlations, so second order moments in a sense. And I showed you that how with some histograms and the posterior predictive fits, how if you use the social relations model, then we can sort of represent those features of the data. But there's all sorts of other features of data sets that we've studied extensively and find interesting. So clustering of nodes, transitivity of nodes, and many, many others. And so we're going to start with, so here variances, covariances, those are based on second order moments. So the next step is obviously a third order moment, something like this, right? So transitivity might be the number of triangles or if you have valued measurements, some sort of sum like this. So here's the trade data. Here's some fit statistics. So if you remember, we had this trade data, and we made posterior predictive samples from the regression model in green for standard deviation of row means, standard deviation of column means, and dyadic correlation. And then we saw how if we move to the social relations regression model now, we can represent those dependencies in the data. But if we move on to another statistic like triadic dependence, both of these models fail, right? So here are the sort of, here's like the third order moment for these trade data, and here's what these models predict for that moment, okay? So the model is not representing this feature of the data very well at all. Here's some other data sets. So here's a neural network of a worm, and so that's a nice looking graph. This is a graph here, and we can fit just a regression model. I guess it's just a Erdős-Rényi graph with no predictors. So that's in green. And then if we use a social relations regression model, now we're accounting for the row and column heterogeneity and the within dyad correlation. So we're getting those. But there is more triadic dependence in this graph than can be explained by the simple row and column effects model. One more network. So there's a protein binding network, and again we see a similar story. These data are symmetric, and so there's no dyadic correlation is meaningless here. So don't worry about this graph here. So again, there's less triadic dependence. There's more triadic dependence in the data than can be explained by either the regression or the Erdős-Rényi graph or the social relations model. Okay, so just for simplicity, let's think about symmetric data for the moment. So what does the social relations regression model translate to for symmetric data? So it's just you have a row effect and a column effect, and they're the same. And if you think about third order moments under such a model, you know that this third order moment is going to be approximately 0 if the AIs are mean 0. So it's not true mathematically. You can find some A's that will make it non-zero, but it's very hard to do that. Well, it's not hard mathematically, but you're not going to get data that are like that. Okay. So if you have this sort of model here, you're going to get third order moments that are about 0. So this suggests we need to have something else. We need to have models with non-additive nodal effects. And so let's just focus on undirected relations in the interest of time. So you might have a model, some regression effects, row effect, or a nodal effect, additive nodal effects, and then some sort of other nodal effects, UI and UJ, and those are non-additive. Those enter the model non-additively in some way. So there's several models of this type, and perhaps the most famous one is the latent class model, also known as a block model. The idea here is that each node I is a member of an unknown latent class, and the probability of a tie between nodes depends only on the classes of the nodes. And so the idea here is you want to estimate the classes of the nodes and the between class rates of ties. And so in this model, nodes in the same class can have a high or small or high probability of ties. So the within class rate can be large or small. So another type of latent variable model or a latent latent node effects model is a distance model. So this is the paper that talked about that. The idea here is that each node I has an unknown latent position, and the probability of a tie depends on the distance between individuals in this latent social space, so to speak. Okay, and so what are the characteristics of this model? So if nodes are nearby one another, okay, so if in this under these latent social positions, that means that they're highly likely to have a tie, right? So if the distance between them is small, it's going to maximize their probability of a tie. But also, if the nodes are close together, then they're going to be close to the same other nodes, okay? So this forces them If you have two nodes that interact, they're likely to be close together. But if they're close together, they're also similar from the perspective of other nodes. So this confounds the within tie density with something called stochastic equivalence. Okay, so this is going to be a problem for lots of graphs. So finally, there's this model, the latent factor model, which a version of which appears in this paper along with the latent distance model, but then I've worked more on it after that. And the idea here is that each node I has an unknown latent factor, and basically it looks like a factor model. So the probability of a tie between two nodes is like the inner product of these latent factors. You can recognize this as sort of looking like an eigendecomposition of some latent matrix. And if you know about eigendecompositions, you know that every matrix has an eigendecomposition. So you should start thinking that maybe this is a very flexible type of model. And it is. So nodes with similar factors could have a large or small probability of ties depending on whether you have positive and negative eigenvalues. Okay. All right. So I think I'm going to skip this part. You can incorporate this stuff into regression models. These different models represent observed features of networks in different ways. So there's two important features of networks, or there's two sort of main features of networks in my mind, one of which is something called homophily, the idea that if two nodes are similar, they're going to have a higher probability of a tie. And there's another one called stochastic equivalence, which says that if two nodes are stochastically equivalent, they interact with the network in a similar way. Okay, so here's a graph on the left, and here's a graph on the right. One of these is supposed to be, these aren't real data, these are made up data. One of these is supposed to exhibit homophily, or explainable by homophily. Okay, and just in the interest of time, it's this one. Okay, so the idea here is this graph has a lot of triangles in it. You could say that people nearby one another have a high probability of a tie. This one, on the other hand, exhibits stochastic equivalence. Here you have classes of nodes like this group here. They're all similar to each other in how they relate in the graph to everybody else, but they don't necessarily have a high within-group rate of ties. Okay, so this is a NIPS paper. I'm just going to tell you the punchline of this NIPS paper. I looked at three graphs. One is a friendship graph. One is a word neighbor graph. And the other is a protein interaction graph. And I did some cross-validation studies. And here's the sort of ROC curve and some predictive, out-of-sample predictive performance checks. And basically, so for the friendship type of network, the distance model did the best, but the latent factor model was close behind, and the latent class model does somewhat poorly. For word neighbor network, the class model fit the best, but the latent factor model fit almost exactly the same, and the distance model did poorly. Then finally, for the protein interaction network, the latent factor model did the best, and the other two were not too far behind. But the reason why, I'm just going to, not total speculation, that this model, these data here exhibit a lot of stochastic equivalence, but not a lot of homophily. These data here represent a lot of homophily, but not stochastic equivalence. The latent class model fits great here. The latent distance model fits great here. But the latent factor model can fit well on both. And that's what's happening in this biological network. There's some parts of the graph where there's lots of like homophily going on. But then other parts, there's these hubs. And things connect to hubs, but hubs don't connect to each other. That's stochastic equivalence and can't be represented by like a latent distance model. Okay. So I'm just going to make one comment, or two more comments. So I do have some mathematical results comparing these different models. And basically, you can look at the types of patterns. This is in this NIPS paper. You can find it on my website. You can look at the types of patterns that are representable by these three models, the latent distance model, the latent class model, and a factor model. And you'll find that a latent factor model with k factors can represent all of the features that a latent class model can represent. This should be obvious because a latent class model is just a low-rank matrix. It's a certain type of low-rank matrix. Interestingly, a factor model with k plus 1 factors can represent essentially all of the patterns you can with a distance model. This is because if you take a bunch of distances and square them, you have a rank 2 model. And then if you do a little bit more work, you can represent all of those with a rank 1 model. And then finally, there are rank 1 factor patterns that cannot be represented by any distance model. Okay? So that's why for a long time I've been trying to tell people about this result, that the distance model is very good when you have lots of homophily in the network, and it does not do so well if you have things like anti-homophily or some sort of stochastic equivalence. And those sorts of patterns can be represented by factor models very easily. So those are very flexible models. Okay, so I've been told to stop, so I must stop there. Thank you.
So because Peter stopped very punctually, we have time for questions.
So just the social relations model, you didn't talk about much about the covariance matrix, which, you know, in network situation is often pretty important. So is what you did, is it just free and you integrate over it, or do you actually
Well, the covariance, in that model, the covariance matrices are very small. So they're just, you have two 2x2 covariance matrices. So you have a covariance. The model is that each individual has a random effect AI and a random effect BI. So we're not looking at correlations between the nodes.
Oh, there aren't. Okay.
Yeah. So I've done some work on that, and that's very challenging because there's very little information there. You can do some stuff. That's stuff with Alex Wolfowski that I've worked on. Yeah.
Just another quick sort of a follow-up about the comparing the different. I mean, I think this is really interesting. But another kind of criterion is interpretability, right, for users. And the distance, I mean, one thing about the distance is when you plot it, it corresponds to what people see cognitively, right? Because the Euclidean distance sort of corresponds to what people see.
I agree. I agree that that's why people like the distance model, and I've been trying to tell people you can plot factors and interpret them also. You just have to think in terms of dot products. But I agree with you. That's the appeal. But there are serious problems with it if you have a data set where you have, say, hubs and spokes, things like that. You just can't represent those features with the distance.
So I'll make an analogy between the question I have has to do with sort of the three-way interactions, the triadic sort of relationships. And you made a point that I hadn't perceived before about that says by going to these models you can capture some of that. But let's talk about the protein-protein interaction. So I know little about protein-protein interaction data, and I do know it's very noisy and messy, but that's all I know.
I'm just going to go to a plot of that.
So I've got protein A and protein B, and if I know protein A and B have already bound, then that changes my thinking about protein C, right? So that's saying condition on some piece of the data, it's going to modify my model. So the analogy is in time series where latent factor modeling, for example, in volatility modeling, is latent process modeling, latent factor modeling. But a lot of other models for the same kinds of data, what we call data-driven models. Condition on certain pieces of data, the model looks different.
Yeah.
So is it your view then, this is just an honest question, that there's a richness in these models already that is enough to capture the structure of protein-protein interactions?
Thank you for asking that. I'm not going to answer your question directly, but it lets me go to my next slide, which is, do these models fit? And so there's two viewpoints, okay? I'm going to sort of answer your question. So here's a model. So the model is that you have a network Y, and your parameters are some rate, some overall density, and these latent factors. And your parameter space includes the overall rate, the eigenvalues, and these latent factors. So if you simulate from a posterior predictive distribution, are you going to get a network that resembles your observed network? There's been some discussion of whether or not latent variable models actually are good at representing these graphs. So, so I'll show you that, in fact, you should believe me in our discussion of these latent factor models that you can make a posterior predictive look very close to the observed data depending on how many latent factors you take. So here's the protein-protein interaction data. Here are simulations from the posterior predictive model, conditioning on, so using the latent factors as parameters in the model. So the answer is yes, these models will fit observed patterns very well as long as you take the number of factors to be sufficiently large. And I'll speculate that for a lot of sparse graphs, that number does not have to be very large at all. For others, it will. But then there's a second perspective, which is sort of also answering your question maybe. If you view these latent factors as random effects, and you have some random effects distribution for them, and you think of the parameters in your model as not including the latent factors, this is like thinking about the model as like a hierarchical model. Then if you simulate from the posterior predictive, then your posterior predictive is only going to look like your observed data in terms of certain features. So if you use, like, this is if you just use sort of standard normal model for the U's. And you get something that doesn't look like your network at all. But this shouldn't be too surprising. If you think about a hierarchical normal model, just the simplest two-level hierarchical normal model, you wouldn't use a normal model for random effects if you wanted to study kurtosis or skew or something like that. It's ridiculous, right? So, my comment for that is that, so there's some new work by Cosma Shalitzi and other people, I believe, that if you estimate this distribution for the random effects non-parametrically, or at least somewhat flexibly, you can get these models at the random effects level to sort of to fit much better. But I'm not sure how to then interpret those. I think you're sort of becoming somewhat circular, but I can talk about that later. Okay.
Right. We have a coffee break now. We start again at 11:30. Let's thank Peter again for the